The second question is an electrochem question, and I am going to use this question to review some of the concepts that we just learned about in the electrochem PowerPoint. Hopefully, it'll help you understand how to answer a question like this. And some of the answers that I will give you are not, you don't have to be as detailed for this particular question, but we're going to use it as a tool to just delve a little deeper into the content you have learned. Okay? So, there's a voltaic cell here. You have on the left side a gold electrode, and on the right side you have an inert platinum electrode. Anytime you have platinum, that's going to be inert. And in the left beaker, you have a 1 molar solution of gold nitrate, and on the right beaker, you have a 1 molar solution of copper nitrate and also a 1 molar solution of copper 2 nitrate. So it is worthy to note that gold will accompany three nitrate ions, and then you'll have the copper is giving you different numbers of nitrate ions as well. Okay, so the first question is to calculate the value of the standard cell potential of this particular voltaic cell. So you would just do E cell is equal to E ox, right, plus E reduction. So you are looking for the one that will oxidize compared to the one that will reduce. Now, both of these numbers are positive in their reduction potentials. Remember, these are for reduction reactions. So the one that will oxidize is the one that will be closer to zero or the more negative one, okay, comparatively. 0.16 is less positive than 1.50. So that is the one that is going to oxidize. However, remember, these are reduction potentials. That means you must flip the equation here. So copper plus is going to oxidize into copper 2 plus, which means 0.16 must be turned into negative 0.16 volts plus 1.50 volts. That will give you 1.34 volts. Okay, so that is the E cell of this actual reaction. It's thermodynamically favorable. Whenever you get a positive E cell, you should think about the fact that if it's positive, it is thermodynamically favorable. Okay, so another thing that should occur to you is that if you have the E cell, now this question doesn't ask for it, I'm just expanding. If you have the E cell, you also have a way of calculating the equilibrium constant for this particular reaction. And that equation is E cell is equal, whoops, what is that? E cell is equal to um, 0.0592 volts over n times your log of the equilibrium constant. So now that you have your E cell, you can just look at the two reduction potential equations, balance those so you can get the correct number of moles of electrons, which is n, and then you can calculate your equilibrium constant. Okay, so anytime you have your E cell in the back of your mind, you should think, okay, I have a way to calculate the equilibrium constant, and I also have a way to calculate my delta G for this reaction, because if they ask you, this reaction is thermodynamically favorable based on your E cell, but can you now calculate the delta G standard for this reaction? You also have a method to do that. Delta G standard for this reaction is equal to minus or negative NF and the E cell. Okay, the N here is the number of moles of electrons, the F is Faraday's constant, and E cell is the number that you just calculated. And the negative sign is showing that that energy is leaving your system. Okay, so you have methods to find three different variables from an electrochemical question: the E cell specific to the voltaic cell, the equilibrium constant, and delta G for that reaction. Okay, this is how things are connected to each other. Okay, now let's look at question or part B. I think I have to go back. Yeah, to get the mouse. All right, so Let me scroll down. The next question is, does the mass of the platinum electrode increase, decrease, or remain the same as the cell operates? And for that, the answer is it remains the same because platinum is an inert electron. It does not participate in the actual reaction. It is just functioning as a method of electron transport. Okay? Now, an expanded view of the gold half cell before the reaction occurs is shown in box A below. And an expanded view of the gold electrode after the cell operates for a period of time is shown in box B below. This is called a particle diagram, and they are super big fans of giving you diagrams at the particle level to interpret. Okay, so whenever you are trying to interpret something like this, you are looking for discrepancies in the numbers of ions or charges of ions usually. Okay, so think about what you saw. Inside this beaker is gold nitrate, and nitrate requires three nitrate ions, and each gold has a plus three ion. So over here, there's a key. Each gold has a plus three ion. So this is plus three, this is plus three, this is plus three. The particle level diagram is nothing but a picture of what a chemical reaction would look like if you were writing it out. And when you are thinking about electrochem equations, you always need to balance not just the actual matter, but also the charge. Okay, so think about charge when you are looking at particle diagrams for ionic compounds and also electrochem particle diagrams. Okay, so this is why you have three nitrates. So there are three nitrates per gold ion. Let's say these three nitrates belong to that one, these three nitrates belong to that one, these three nitrates belong to that one. So this is before the reaction happens. After the reaction happens, you can see two of the three plus charges have attached and become gold ions on the side. Okay, so now we have these two, AU, no charge, and this one is still a AU plus 3 charge. Okay, and these three nitrate ions, let's say go with this one, and to replace the lost positive charge, potassium ions have come in. However, it's no longer balanced in terms of charge. We had a plus 9 charge here, and over here we only have 3, 4, 5 plus 5 charge compared to the 9 minus charges that you had on the box A on the left side. And right now you have 9 minus charges here as well. However, you are missing some plus charges. So that is what is wrong with this particle level diagram. Okay, the charges are not balanced. Stoichiometrically, the charges must be balanced. So there must be more potassium ions that came to replace each of the gold ions that were lost. If you had six potassiums, you would be good to go. Okay, so that was what was wrong with the picture. Now, let's look at the next question. C was assuming that the representation in box A is accurate. Explain what is wrong with the stoichiometry represented in box B. Box B does not stoichiometrically account for the lost positive charges of the gold ions. There should be more plus charge potassiums coming in to replace those. Okay, so Part D. After the cell has operated for 30 minutes, 0.185 grams of gold is deposited onto the gold electrode. Number one, calculate the number of moles of gold deposited. So that's super easy. You got 0.185 times grams of gold times, I need the molar mass of gold from your periodic table. That is 196.97. That's going to be 196.97 grams of gold on the bottom for every 1 mole of gold. That gives me, let me just do that, 0.185 divided by 196.97 gives me 9.39. Let's see, how many sig am I looking for? 3 sig. Yeah, okay. Times 10 to the negative 4 moles of gold. Okay, so that was easy. And then the second one is to calculate the average current that passed through the cell during the deposition of solid gold. So think about it this way. I told you that you can be given a current and a time, and you are asked to calculate the mass. But here they have given you mass and time, and they're asking you to calculate current. Any type of stoichiometric calculation with electrochem is going to give you time that the current passed, or time that it took for some mass to deposit. So time is a common factor. The one that will be missing is either current or mass. One of them will be given to you. Okay? So those are the only questions in Stoic. So they're relatively easy to calculate. So we have 9.39 times 10 to the negative 4 moles of gold, right? And we need to find a way to go from moles of gold to charge. Okay, so the two things that you are going to use for any stoichiometric calculation is going to be Faraday's constant, 96,000 times 96,485, 495, I think. I forgot. 495, 485. Let's check. 485. I was right. Okay. 485 coulombs of charge per 1 mole of electron. Okay, and then you have to actually find the number of moles of electrons that gold is using, and that's actually in the half reaction above. I'm not gonna scroll up because this thing is like kind of annoying to scroll up with the tools over here. So gold has a +3 charge, so clearly it is taking in 3 electrons to become solid gold. So the number of moles of electrons is 3. So we have 9.39 times 10 to the negative 4 moles of gold here. That is our starting point. 9.39 times 10 to the negative 4 moles of gold. And I am going from that to moles of electrons. So for every 1 mole of gold, right? For every 1 mole of gold, based on this equation, this is gold solid. So for every 1 mole of gold, right there, I'm using a 3 moles of electrons. So it's 3 moles of electrons. And now I need Faraday's constant. I have 96,485 coulombs of charge for every 1 mole of electrons. And now I can do some unit cancellation here. Moles of gold cancel out, moles of electrons cancel out, leaving me with coulombs of charge. So let me calculate that. 9.39 times 3 times 96,485. Okay, so that gives me 271.864. I'm just going to give a bunch of decimals here. Coulombs. And now we need to figure out current. So current is in the units of amps. 1 amp is equal to 1 coulomb per second. I have coulombs. I need seconds. How do I find seconds? I look at my time here. 30 minutes into seconds, okay? 30 minutes times 60 will give me seconds. 1800 seconds, because 60 seconds is in 1 minute, okay? So I'm just going to divide this by 1800 seconds. Or, do I have an eraser? I don't want to mess with it. Okay, so 1800 seconds, 271.864 divided by 1800 gives me 0.151 coulombs per, okay? And that is the number of amps that I have. There we go. Let's check our calculations just to be sure. 9.39 times 10 to the negative 4 is times by 3, then that's times by 96,485, and that is divided by 1800 seconds. Yeah, we good. So 0.151 amps is what is flowing through this when the gold was deposited, okay, for 30 minutes. All right, so the next question has a little bit of a setup. The student adds some sodium chloride to the half cell that contains copper plus and copper 2 plus, and a precipitate forms based on the information on the table below. So let's get the table below. Oops. All right, table below. Identify the precipitate. Justify your answer with a calculation. Okay, so they don't want you to they don't want you to compare KSPs. No, you shouldn't compare KSPs. Not that they don't want you. They want you to go down that road, but you can't compare the KSPs. Okay? So they have given you copper chloride, copper 1 chloride, and copper 2 chloride. And when sodium chloride is added, one of them is going to precipitate, not copper, not both of them, but one of them. And that one of them is going to be based on the molar solubility and not the KSP values. Here's a reminder: KSP values between ionic compounds cannot be compared if they do not generate the same number of ions. Copper 1 chloride generates 2 ions, copper 2 chloride generates 3 ions. The KSPs cannot be compared. However, their molar solubilities can be compared because molar solubility for both is like the X, and that's one ion solubility, so you can compare the solubilities. So, if the KSP for copper 1 chloride is given, that means 1.7 times 10 to the negative 7 is equal to x squared. You're looking for x, so square root of 1.7 times 10 to the negative 7 is equal to x. Let me see what it is. 1 point, whoops, second, 1.7 times 10 to the negative 7 gives me 4.12 as my molar solubility. 4.12 times 10 to the negative 4 as my molar solubility. Okay? This is going to be molarity. 4.12 times 10 to the negative 4 is a much smaller than 5.2, and therefore copper 1 chloride will precipitate out first. This will precipitate out first. Determine the identity of the precipitate. It's copper 1 chloride. Write the net ionic equation for the formation of the precipitate. That's easy peasy. You have Cu plus 1 plus Cl minus 1 going to CuCl solid. And these should be AQ and AQ. Net ionic means you don't need to use sodium because sodium is a spectator ion. Okay, now the next question is a good question to explain things and remind you of things. Okay, the student predicts that the cell voltage will increase after the precipitate forms. Do you agree with the student's reaction or student's prediction? Justify your answer. So, let's look at our voltaic cell. This is why I reminded you of the two questions, or no, not two questions, two equations um, regarding E cell, what you can do with E cell. Okay, so here's what is occurring. You have copper 1 nitrate and copper 2 nitrate, both adding copper ions into solution. When the student adds sodium chloride in there, okay, the chloride will precipitate out with the copper ions that are floating. Okay, now when that happens, the student is saying that the voltage would increase because the precipitate is forming. Okay, but that's not true. The voltage cannot increase. Oh, I hate this. These tools are terrible, but I have no other way of writing on this. And as you know, the PDF doesn't save any of the pictures, so that's no good. The student predicts that the cell voltage will increase after the precipitate form. Do you agree with the student's prediction or not? Justify your answer. Now, I want to show you guys something. I want to show you the scoring guidelines here. Oh, can I select the scoring guidelines? Let's try to find the top of the page. Okay, here it is. There it is. Okay. So I want to show you. Oh no, I don't want to generate anything. I just want to show the scoring guideline. Oh my gosh. Just fast forward through this, okay? I'm literally just trying to select this arrow. There we go. I want to show you the answer that they gave you guys, and that is kind of all that is expected. Wait, where is it? Hello? Okay, here it is. Let's scroll down. They should be down here. So this is part G. Right? Part G, part G. Yeah, okay. Just fast forward through this, okay? All right. Okay. We just calculated this. That was good. This was good. 0.151 amps or coulombs per second. That was good. And then over here. Please repeat the correction. Yes, the internet is down. We're working on it. We're working on it back up. Thanks. Oh my gosh, let's hope Screencastify doesn't crash in the mid of my video, right? Okay, so if it does, I'll explain this in another video. Just fast forward, okay? All right, so here is the line of work that is required for part F. Disagree. The precipitate will decrease copper plus, which will cause Q to increase and become closer to the value of K. Therefore, the voltage of the cell will actually decrease. Now, this is enough for this particular question. However, for this particular question, I will explain to you why this is so, because I feel like this is not the clearest explanation. The disagree part is obviously correct. You can disagree with the fact that the precipitate will decrease, okay? The precipitate will decrease the voltage. Let me hide this. So here is what is happening. When you add sodium chloride, the copper 1 ions are going to precipitate out. Not the copper 2 ions, the copper 1 ions are going to precipitate out. In your original equation, okay, you have, or if you did an original equation for the reaction that's happening inside this cell, you would have this. If you add the half reactions up, you would have, in a balanced chemical equation, 3 copper plus plus Au 3 plus goes to 3 coppers 2 plus plus a solid. All of the other ones are aqueous. Okay, you have 3 copper plus ions, copper 1 here, which is being oxidized into copper 2. So copper 1 is losing electrons and becoming copper 2. Okay, gold is taking the electrons lost from that copper and becoming solid gold. So gold is being reduced, copper 1 is being oxidized. When you remove copper 1 ions from solution, you are going to be removing your reactants. Okay? Now think about what an equilibrium constant or a Q value would be. Q would be the concentration of copper 2 plus cubed over the concentration of copper 1 plus cubed over times the concentration of gold with a plus 3 charge. That is what your Q value would be. When you add sodium chloride, you are going to remove copper 1, because remember, copper 1 chloride is precipitating out of solution. Okay, so copper 1 chloride is being removed, so that means this concentration is going down. Your reactant concentration is going down. When your reactant concentration goes down, your Q value is going to go up. Okay, because the ratio is changing, right? So you can calculate what the equilibrium constant for this reaction should be using your E cell value. Okay, so the top equation here you can use to calculate K. And when I calculated K, I got a K of 8. The equilibrium constant for this reaction is 8. Okay, 7.9 for something, but it was still 8. When the concentrations were what it is originally. Okay? Now, yeah, 7.94. If I reduce the amount, so if I have 1 molar here, okay, and that's cubed, that's from over here, right? 1 molar of copper 2 nitrate right there. And I have 1 mole over here, and that's from here, of copper ions. And I have 1 molar over here, and so this is cubed and this is not cubed. So it's 1 cubed over 1 cubed times 1. That is equal to 1, a Q of 1, right? Now, if I reduce the amount, let's say I'm going to halve the amount of copper 1, and I say 1.0 cubed, copper 2 plus is not changing, but I'm going to make copper 1 plus half of what it was, and because half of it has precipitated out with the chloride, if you calculate this number, this is actually 8. Okay, if you calculate this out, 1 cubed over zero point 0.5 cubed times 1, that's 8. So your Q used to be 1, and if you reduce the concentration of copper 1 ions, your Q increases, and if your Q increases, you get closer to your equilibrium constant. Closer to your equilibrium constant means the voltage does not increase. If your reaction reaches equilibrium, there will be no current flowing. There will be no moles of electrons. Okay, no net moles of electrons will be going to one side to deposit and make solid gold. So the closer you get to your equilibrium constant, the worse your battery is. So that explanation, that one line, this is what it is based on. Your reactant concentration goes down, therefore your Q value increases, and therefore your voltage does not increase when the precipitate forms in this particular case. The precipitate will decrease the amount of Q plus, I mean, not Q, I just read this as Q, copper plus 1, which will cause your reaction quotient to increase and become closer to the value of K. Therefore, the voltage of the cell will decrease when the precipitate forms. Okay? That was a long explanation.